Okay, so in topic 3.3, so we're going to discuss a topic on logarithmic functions. So previous two subtopic we have discussed about exponential or index, and now we're going to discuss the opposite operation that is called as being logarithmic function. So basically, logarithmic function, as I mentioned just now, it's going to be an opposite operation of exponential. So what is opposite operation? For example, if I have an equation of a is equal b plus c, and I have a plus operation over here, and if I wanted to move c to the other side, so what happened is that, so my equation is going to be a minus c equal b. So when I move to the other side, so the opposite operation happens, so plus now become a minus. And it will be the same idea for the case of multiplication as well. For example, if I have a is equal b multiplied by c, so if I were to bring c to the other side, so the opposite operation is going to occur. So the opposite operation for multiplication, that will be division. So I'm going to have a over c, that is going to equal b. So previously we have multiplication, so now it become division because those two operations are the opposite of each other. So that will be the same idea for the case of logarithm as well. So basically the logarithm function, so it is going to be a function that is opposite to exponential or index. Okay, logarithmic function is the function given in the form of x equal log of b to the base of a. So this a over here, so it's called as being the base. Okay, so this is what it's called. So it's going to be a base. And what happens is that the value of a, so it's going to be a is a value that is greater than 0. Okay, however, a cannot be a value of 1. Okay, so you can have any base, for example, so it could be 1 over 2, it could be 1 over 3, it could be a value of 2, as long as it is a positive number greater than 0, not including 0, and a cannot be a value of 1. So those are the conditions. And as I mentioned just now, a is called as being the base. So if we were to recall what we have discussed in the index also have base. For example, if I have an equation of y equal k to the power of c, so the number that I raised to the power over here, so which is k for this case, so this is going to be the base. So both index and logarithm has base. For the case of index, so whatever number that we raise to any power, so that is called as being the base. And for the case of logarithmic function, so whatever that goes between log and the number, so in between them, that is going to be called as being the base. And as I mentioned over here, so the base value of a must be a positive number and it cannot be a value of 1. And for the case of b, so there's also restriction on value of b. So b must also be greater than 0. So greater than 0 means that it should be a positive number. And for the case of b, it cannot be equal 0, because what happened is that if I have log of 0, if you use your calculator for this, you can try it on your own and verify that. What happened is that you will be given math error on the screen, so which means that log 0 is actually undefined. So that there is what I call that. So log of 0 never exists. You cannot find the log of a 0 number. So therefore, so b cannot be a value of 0 and a cannot be a value of 1. And what happened is that, so logarithmic and index, they are interchangeable. So this is going to be interchangeable. If I have this as the index form, I can change that. It is going to become this in terms of the logarithmic form. So this is going to be the index form and this is going to be the log form. Okay, so what happened is that if I have the case of index, so a is going to be the base, and when I change it to log form, so it's still going to be the same. What happened is that a is going to be the same of our logarithm, and x over here, the power, is going to come down. So here my x going to be by itself on the other side of the equation, and a is going to move to the other side and become the base. Okay, let me show you a couple of examples. So let's say if I have something like this, so log of c to the d. So let me put it the other way around. Okay, let's say if I have a to the power of b is going to equal c. So what happens now, what is going to be my base? My base is going to be a. So I'm going to move it to the other side. So when I change it to logarithm form, it's still going to be the base, but now b is going to come down. So I'm going to have b is going to equal log of c base a. Okay, so that is how it goes. Or it could be also the other way around. So let's say if I have a log of ef is going to equal g. So when I change this into index form, so this e over here, so which is my base, is going to be transferred to the other side, and it's still going to be the base. So it's going to be f is going to equal e raised to the power of g. Remember? So when it is the base, when you move to the other side and it become from log to index, it is still going to be the base. So that is how it goes. And of course, the base could be anything. So base could be any number except for that it cannot be a value for 1. So the most common base that we use is going to be the base of 10. So there are multiple ways of writing base of 10. You can write it as log of base 10. You can write it as log of x, so without anything written in between. So we know that is supposed to be log to the base of 10. Or you can also write it in the term of lg. When you have lg, automatically we know that is also log to the base of 10. But other than that, it should be written. For example, if I have log of 2x, then I have to write the 2. Or else, if it's not written, for example, if you come across something like this, so log of x, so this is actually represent log of x to the base of 10. If it's not written, automatically it will be a base of 10. But if it's some other base, then it should be written like what I had over here. Okay, so then beside base 10, so the most common base that we use is the natural logarithm, so which is going to be the base of e. So we have seen in index before, e, basically it is just a number. So if you press your calculator, you will get that e is going to be some number which is 2.71 something, if I'm not mistaken, right? So basically, instead of writing it as a number of 2.71, like you know what happened for pi, so we write it as being a number that is called as e. Okay, and for the case of natural logarithm or base of e, so you can either write it as log with base e or the ln. And I did mention this to you before, I think in the previous video, the fact that ln is actually not ln, only we Malaysian pronounce it as ln. As I was doing my degree in New Zealand, I was being scolded once by my German lecturer because he said that there's no such thing as ln. It is actually ln is actually log to the base of e, so pronounce that as being log. So that is why you're going to hear me pronouncing ln as log throughout the course. Okay, so basically the two most common base is going to be base of 10 and also base of e. So now let's look what we have over here. So these are going to be the example. So what we're going to do is we're going to convert the following to logarithmic function, logarithmic form. So we are given this function over here, so which is in term of index. So I'm going to change it in term of logarithm form. So let me add another page down here. So let's start with a. Right, for the case of a, so this is going to be question number 1, a. So for a, I have y equal 5 to the power of x. For this case, what is going to be my base? So my base is going to be 5. So whatever that goes beneath the power, so my power is x, anything that goes beneath that, so that is going to be the base. So when I change this to logarithm form, it's still going to be the base. So now I'm going to move it to the other side. So now what happens is that I will get log of base 5 y, that is going to equal x. So that's what happened when we change it to logarithm form. And for b, I have 4 to the power of 2 is equal to 16. Okay, this is true. 4 to the power of 16 is indeed equal to 16. And for this case, our base is going to be 4. So when move it to the other side, so what happened is that I will get, so 2 is going to equal log of 16 base 4. Okay, so that is how it goes. We know that, yes, in fact, that when I have log 16 base 4, it is indeed going to equal 2. And the third one, so I have p equal exponential to the power of q. to the power of q, what is going to be my base. So now I have a natural, well, that's not a highlighter, so e is going to be my base. I'm going to have a natural log for this case. So therefore for this case I'm going to have log of p to the base of e, so that is going to equal q. Okay, so basically whatever that start with a base on index, when you change it to log, it's still going to be the base. So that is question number 1. What about question number 2? So it says convert the following to index form. So for question number 2, so I am given logarithm form and we're going to change this to index form. So it's going to be the other way around from what we have done before. So let me add another page for this and paste it here. So I'm going to make it super large so we can scribble on it. Okay, so it's still going to be the same idea. So now what happened is that my base is going to be E2. So I'm going to change it to index form. So I'm going to have 32. So that is going to equal 2 raised to the power of 5. So which is actually true. So if you use your calculator to find 2 to the power of 5, that is indeed going to be 32. And it's going to be the same for B. So what happened for B is that the base is given by a value of 3. So when I change it to index form, so I'm going to have 1 over 81. So that is going to equal 3 to the power of negative 4. And again, if you press your calculator for 3 to the power of negative 4, it is indeed going to give you 1 over 81. And the last one, so here what happened is that my index, my base value is going to equal 8. When I change it to index form, I'll have that 16 is going to equal 8 to the power of 4 over 3. Okay, and again, if you evaluate 8 to the power of 4 over 3, then you will get a value of 16. So let's see. So next we're going to have a look at the graph of logarithmic function. So the thing about logarithm function is that, so domain is actually a value of x. So this is our equation. So we have an equation of y is equal log of ax. So what happened with the value of x is that x must always be a positive number. So it must be always a positive number. So we cannot find the log of a negative number. It doesn't exist. So that is why. So the domain is going to be from 0 to infinity. And again, as I mentioned to you before, so the fact that we cannot find log of 0. So that is why for this case, 0 is not included. Because when we have log of 0, that will be undefined. So there is no way we can find log of 0. So for the case of the domain of logarithm function, so it will be from 0 until infinity. And for the case of range, so the range, the value of y, when you log a function, it could be any value, negative value, it could be a positive value. So that is why the range is going to be from negative infinity until infinity. So graph has x-intercept at 1, 0. So x-intercept, we know that this is going to be the case when y is equal 0. So basically what happened is going to be something like this. So let me add a paper. So you have an equation of y is going to equal log of ax. So x-intercept is when y is equal 0. When y is equal 0, we will get log of ax is going to equal 0. I want to change this to index form. So x is going to equal a to the power of 0. And we know that anything raised to the power of 0 is simply going to be 1. So that's why. So the intercept is going to be at 1, 0. Okay, so and the asymptote, what happened is that, as I mentioned to you before, so log of 0 is undefined. So let me put over here. So log of 0 is undefined. So that is why, so we're going to have an asymptote at x equal 0. So x is equal 0 is equivalent to the y-axis because log of 0 is undefined. So we're gonna have asymptote right there. And for your graph, what happened is that when the value of base, so base is greater than 1, so the graph is going to increase. And when your base value is a fraction, so value that is between 0 and 1 is going to be a fraction. So it could be a value of 1 over 2. It could be a value of 1 over 3, 1 over 4, and so on. Anything that is between 0 and 1, so the graph is going to decrease. So here I have a graph that actually shows such a case. So let's start with the green one. So the green one over here is actually log of x, and we know that if the base is not written, so we're going to assume that is going to be 10. So for this case, so let me put it somewhere over here. So this is actually equivalent to log of 10x. So our base is a value of 10, so it's going to be the case when a is greater than 1, and we know that if when a is greater than 1, the graph is supposed to be increasing, and the intercept is going to be right here, which is at 1 0. Okay, however, so we're going to have an asymptote. This is our asymptote, so this is where x equal 0 is, so you cannot cross that line, and we cannot find log of a negative value. So that is why it's going to start from 0 until infinity, but not including 0. Okay, so that is going to be one example, and I have another two examples. So the blue over here, so this is written in the form of log x over log 0.5. So this is actually something like this. So y is going to equal log of x over log 1 over 2. But I'm not going to explain this to you yet. I'll explain this to you later. So basically, if I were to change the form, so this is actually a graph of this is equivalent to log of x to the base of 1 over 2. For this case, basically, so the base is going to be 1 over 2. And we know that the base of 1 over 2, so this is less than 1. So it's going to be between 0 and 1, in fact. So let me clear this. So our base is a value that is between a and 1, and the graph is supposed to be decreasing. So that is what happened over here to the graph in blue. So my graph is actually decreasing. It's going down, and of course it cannot intercept at x equal 0. And the last one in green over here is actually y equal log x over log 2. And this graph is actually equivalent to, this is actually a graph of log x over, so it's not log x over, it's actually log x to the base of 2. And for this case, what happened is that, so our base is going to be a value of 2, and this is when a is greater than 1. So our value of a is greater than 1, the graph is going to be increasing, and this is what happened with the red graph. It's actually increasing and intercept at 1 0. Okay, so that is going to be the idea of graph of logarithm. So how does log x over log a half become this? Okay, so I'm not going to mention this, but later in the next section, when we discuss about property of logarithm, you will know why is log x over log half equal log of x base over half. So it's basically because of the formula when we change the base. But the main point I would like to highlight to you the fact that if our base value is greater than 1, and the graph is going to be increasing, and if it's a value between 0 and 1, which is going to be a fraction, so it's going to decrease. So that is going to be the important idea here. Alright, so as we have seen in chapter number 2, so what happens is that if I have a function f of x, and if I want to find the inverse or the graph of the inverse of the function, so I have f of x, and I'm going to find the f inverse of that function. And how do we sketch that? So all we have to do is we have to reflect the graph f of x on y equal x. So this is what happened over here. So I have a function f of x equal 2 to the power of x. So let me show you like what happened when we find the inverse. So remember, how do we find inverse in chapter 2? So if I have y equal 2 to the power of x, then I'm going to have x is going to equal log of y to the base of 2. So my f inverse of x is going to equal log 2x. So this is, remember, this is how we find inverse. So first we're going to let y, and then we're going to find x, step number 2, and then we change it in terms of f inverse x. So this is what happened over here. So basically these two functions, they are the inverse of each other. So f of x equal 2 to the power of x, and y equal log 2 of x, log x to the base of 2. So if I have the graph of 2 to the power of x, then all I have to do is reflect that on the y equal x line, which is right over here, and then I will get the graph of the inverse. So this is what happened. So this is how the graph of index and logarithm looks like. Okay, next we have a bunch of exercise over here. So what we're going to do is I'm going to discuss this with you in class later next week.